Throughout my life as a physicist, I have been asked countless times to explain what atoms really look like, how electrons truly move, what is actually happening inside matter at the smallest scales. People want pictures, visualizations, something they can hold in their mind's eye and say, yes, that is what reality looks like down there. And I must tell you, with some regret but also with deep conviction, that nature refuses to give us such pictures. Not because our instruments are inadequate, not because our theories are incomplete, but because the quantum world simply does not operate in a way that can be captured by the kind of clear, definite, visualizable pictures that work so well for describing the everyday world around us. This is not a failure on our part. It is a profound truth about nature herself, one that took me decades to fully appreciate and articulate. Let me take you through this journey, because understanding why nature refuses clear pictures is essential for understanding quantum mechanics, and I would argue, for understanding the limits and possibilities of human knowledge itself. When I was young, studying physics at the turn of the 20th century, we had wonderfully clear pictures of what atoms might be. Some imagined them as tiny billiard balls, solid and impenetrable. J. Thomson, after discovering the electron, proposed what people mockingly called the plum pudding model, where electrons were embedded in a positively charged sphere like raisins in a dessert. These were clear pictures. You could draw them, visualize them, imagine reaching out and touching these tiny objects if only you had small enough fingers. Then came Ernest Rutherford's revolutionary gold foil experiment. By firing alpha particles at thin gold foil and observing how they scattered, Rutherford discovered that atoms have a tiny, dense nucleus with electrons somehow arranged around it. This immediately suggested a new picture, the planetary model, with electrons orbiting the nucleus like planets around the Sun. This was an even clearer picture, one that made intuitive sense because we already understood planetary motion. Surely the atom was just a miniature solar system. But there was an immediate and fatal problem with this picture. According to Maxwell's equations of electromagnetism, which had been brilliantly confirmed by countless experiments, any charged particle that accelerates must radiate electromagnetic energy. An electron orbiting a nucleus is constantly changing direction, constantly accelerating, and therefore should constantly radiate energy. This means every electron should spiral into the nucleus in a tiny fraction of a second, and every atom should collapse almost instantly. But atoms are stable. They have existed for billions of years without collapsing. Something was deeply wrong with this clear, intuitive picture. This was the crisis that consumed me when I went to work with Rutherford in Manchester in 1912. I was convinced that the nuclear model was correct, that the experimental evidence was too strong to ignore. But I was equally convinced that classical physics, with all its clear pictures and deterministic laws, could not account for atomic stability. I realized we needed to import the quantum idea that Max Planck had introduced for radiation and that Einstein had extended to light. Perhaps the quantum was not just a mathematical trick but a fundamental feature of atomic physics. My solution was to propose that electrons could not orbit at arbitrary distances from the nucleus but only in certain discrete, quantized orbits. In these special stationary states, the electron would not radiate energy despite accelerating. This violated everything we knew from classical electromagnetism, but it solved the stability problem. When I calculated the allowed energy levels for hydrogen and predicted the wavelengths of its spectral lines, the agreement with experiment was stunning. But what kind of picture did this give us? I still spoke of orbits, and I could draw diagrams showing circular or elliptical paths for electrons. But these were not really classical orbits because the electrons did not radiate while in them. And electrons jumped instantaneously from one orbit to another without passing through the space between. These quantum jumps had no classical analog. They were discontinuous, instantaneous, unvisualizable. I could draw the before and after states, but I could not draw the transition itself because there was no trajectory, no continuous path. Even as I celebrated the success of this model, I knew it was intellectually unsatisfying. I had grafted quantum rules onto classical concepts in an ad hoc way. The model worked, but it was not a proper theory built from fundamental principles. It was a hybrid, a transitional step towards something deeper. And that something deeper, when it emerged through the work of Heisenberg, Schrödinger, and others in the mid-1920s, made the situation far more radical. Werner Heisenberg developed matrix mechanics, a formulation that abandoned orbits entirely. He insisted that physics should deal only with observable quantities like energy levels and transition probabilities, not with unobservable things like electron trajectories. His mathematics worked brilliantly but gave no picture at all of what was happening. Around the same time, Erwin Schrödinger developed wave mechanics, treating the electron not as a particle but as a wave described by a wave function. Now we had a different kind of picture, but it was equally strange. The wave function spread out through space, and its square gave the probability of finding the electron at different locations if you measured it. Here is where nature truly begins refusing clear pictures. In Schrödinger's formulation, before you measure an electron's position, it does not have a definite position. It is not secretly somewhere with you just being ignorant of where. Rather, the electron is in a superposition, potentially present at many locations simultaneously, with the wave function encoding the probabilities. Only when you measure does the wave function collapse, and the electron manifest at a specific location. But what does the electron look like before you measure? There is no picture. It is spread out, but not like a physical wave of matter. It is described by a mathematical wave function that is not itself a physical object but a representation of quantum possibilities. I spent many hours discussing these puzzles with Heisenberg in Copenhagen. We would walk along the beach or through the streets, arguing about how to interpret the mathematics, what it meant for our understanding of nature. I came to realize that the problem was not with quantum mechanics, but with our insistence on having clear pictures. We were trying to force quantum phenomena into classical conceptual frameworks that simply did not fit. This is when I developed the concept of complementarity, which became central to what people call the Copenhagen interpretation of quantum mechanics. I argued that quantum objects like electrons have multiple aspects that are all necessary for a complete description but that cannot be visualized simultaneously. The electron has wave properties and particle properties, but you never observe both in the same experiment. If you design an experiment to reveal wave behavior, like passing electrons through two slits and observing interference, you cannot simultaneously determine which path each electron took. If you modify the experiment to track the particle path, the interference pattern disappears. These are not two different pictures that you can somehow combine into one complete picture. They are complementary aspects that require mutually exclusive experimental arrangements to observe. You can have one picture or the other, but never both at once. And neither picture alone is complete. You need both to fully describe the electron, but nature refuses to let you see both simultaneously. Let me give you another example that shows why clear pictures fail at the quantum level. Consider the simple question, where is an electron in an atom? In my early model, I could draw an orbit and say the electron is somewhere on this circular path. But quantum mechanics says the electron is described by a wave function that spreads out around the nucleus. The probability of finding the electron is high in certain regions and low in others. But before you measure, the electron is not at any definite location. It is in a superposition of being in many places at once. Now, you might object that this is just ignorance, that the electron really is somewhere, and we just do not know where until we look. But quantum mechanics says something far more radical. The electron does not have a definite position until you measure it. The act of measurement does not reveal a pre-existing position. It brings a definite position into existence from the spread-out quantum possibilities. This is not a picture you can draw or visualize in any classical sense. How do you draw something being everywhere and nowhere at once? How do you picture the transition from quantum superposition to definite classical outcome? Heisenberg's uncertainty principle makes this even more explicit. You cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you determine one, the less precisely you can know the other. Now, if these were just practical limitations on measurement, we might still maintain that the electron really has a definite position and momentum, and we are just unable to measure both. But that is not what the uncertainty principle says. It says that position and momentum do not both have definite values simultaneously. They are represented by mathematical operators that do not commute, meaning they cannot both be measured precisely at the same time because they correspond to complementary aspects of the quantum state. So what picture do you have of an electron that does not have definite position and momentum simultaneously? There is no classical picture that captures this. You can draw a wave function as a graph, showing probability amplitudes at different positions, but this is a mathematical representation, not a picture of what the electron looks like. The wave function itself is a complex valued function, not something you can directly visualize like a water wave or a piece of string. I argued extensively with Albert Einstein about these matters. Einstein desperately wanted to maintain clear pictures, to believe that quantum mechanics was merely describing our incomplete knowledge of an underlying definite reality where particles have all their properties at all times. He proposed clever thought experiments trying to show that quantum mechanics led to contradictions or paradoxes that could only be resolved by introducing hidden variables that would restore clear pictures. The most famous was the EPR paradox, where Einstein, Podolsky, and Rosen argued that quantum mechanics predicted instantaneous influences between distant particles, what Einstein called spooky action at a distance. They thought this was absurd and must mean quantum mechanics was incomplete. I responded that the problem was with their insistence on maintaining a classical picture where particles have definite properties independent of measurement. Quantum mechanics describes correlations between measurement outcomes, not underlying properties that exist whether you measure them or not. Decades later, John Bell developed a mathematical test that could distinguish between quantum mechanics and any theory with local hidden variables that would give clear pictures. Experiments have consistently confirmed quantum mechanics and ruled out local hidden variables. Nature truly does not provide the kind of definite, visualizable reality that Einstein hoped for. The refusal of clear pictures is not a temporary limitation but a fundamental feature of quantum reality. But why does nature refuse clear pictures? I think it is because our notion of clear pictures is based entirely on experience with macroscopic objects that never exhibit quantum behavior in obvious ways. We see chairs and tables and planets that have definite positions, that follow continuous trajectories, that never seem to be in two places at once or in superpositions of different states. These macroscopic objects do obey quantum mechanics, but they interact so strongly with their environments, with light and air molecules and thermal radiation, that quantum coherence is destroyed almost instantly. What remains is effectively classical behavior. This process, which we now call decoherence, explains why we never see quantum superpositions of macroscopic objects. It is not that quantum mechanics stops applying above some size scale. It is that the distinctive quantum effects, the superpositions and interferences that make quantum mechanics strange, get washed out by environmental interactions. The information about quantum phases gets dispersed into the environment in such a complex way that it can never be recovered to show interference. What remains are classical probabilities rather than quantum amplitudes. So our clear pictures work for large objects because quantum effects are suppressed by decoherence. When we try to apply these pictures to small, isolated quantum systems where decoherence is minimal, the pictures fail because we are seeing quantum mechanics in its raw, undiluted form. The electron in an atom is not constantly being measured by its environment. It can maintain quantum coherence, existing in superpositions, and this is precisely what makes the pictures impossible. Some people find this deeply frustrating. They feel that physics should give them mental images they can manipulate, clear pictures of what is really happening. But I came to see this differently. The refusal of clear pictures is itself a deep insight into nature. It tells us that the microscopic world is not just the macroscopic world made smaller. It is qualitatively different, operating according to quantum principles that have no classical analog. Our visualization ability is adapted to the classical world where we live. It is not a reliable guide to the quantum realm. This does not mean we cannot understand quantum mechanics. We can understand it mathematically with great precision. We can calculate probabilities, predict experimental outcomes, design technologies based on quantum principles. But this understanding is not the same as visualization. It is more abstract, more mathematical, and in some ways deeper because it captures regularities that no picture could contain. Let me give you a concrete example of how this works in practice. When chemists want to understand how atoms bond to form molecules, they use quantum mechanics to calculate electron wave functions for different molecular configurations. These wave functions spread out over multiple atoms, creating regions of high and low electron probability. The shapes of these orbitals, as we call them, determine chemical properties. We can draw these orbital shapes, and they are useful guides for chemical intuition. But they are not pictures of where electrons are. They are representations of probability distributions. The electrons are not little balls sitting in these orbital shapes. The orbitals are the quantum states themselves. Or consider quantum tunneling, where particles can pass through energy barriers that classical physics says should be impenetrable. How do you picture this? Does the particle dig a hole through the barrier? Does it momentarily borrow energy to jump over? No picture like this makes sense. What happens is that the wave function extends into the classically forbidden region, and there is a small but non-zero probability of finding the particle on the other side if you measure there. The particle does not travel through the barrier in any classical sense. It is a purely quantum phenomenon that has no visualizable mechanism. Throughout my career, I tried to help physicists accept this new reality where clear pictures are unavailable. I emphasized complementarity, the idea that we need multiple mutually exclusive descriptions to capture quantum phenomena completely. I emphasized the crucial role of measurement in bringing classical definiteness out of quantum indeterminacy. I emphasized that physics is about predictions and observations, not about constructing metaphysical pictures of unobservable realities. Not everyone was convinced. Some physicists developed alternative interpretations of quantum mechanics that tried to restore clearer pictures. David Bohm created a theory with hidden variables where particles have definite trajectories guided by a quantum potential. Hugh Everett proposed many worlds, where every quantum measurement causes the universe to split into branches corresponding to different outcomes. These interpretations are mathematically consistent and make the same predictions as standard quantum mechanics, but they seem to me to introduce unnecessary complications to avoid accepting what quantum mechanics is plainly telling us. The pictures that Bohm's theory provides, with particles following complex, non-local trajectories influenced by quantum potentials, are not really the clear, intuitive pictures that motivated the search for hidden variables in the first place. They are strange and convoluted, making the theory more complex without providing real explanatory advantage. And the many worlds interpretation multiplies entities beyond necessity, positing an infinity of unobservable parallel universes to avoid accepting that measurement plays a special role in quantum mechanics. I remain convinced that the Copenhagen interpretation, with its emphasis on complementarity and the limits of visualization, captures what quantum mechanics is really telling us about nature. Yes, it requires us to give up the dream of clear pictures. Yes, it places measurement in a special, somewhat mysterious position. Yes, it embraces fundamental uncertainty and randomness. But these are not defects. They are features of quantum reality that we must accept if we want to understand nature as it truly is. Why does nature refuse clear pictures? Because clear pictures require definite properties that quantum systems simply do not have before measurement. They require continuous trajectories that quantum jumps violate. They require that we can visualize all aspects of a system simultaneously, but complementarity shows that different aspects require mutually exclusive experimental arrangements. They require a separation between observer and observed that quantum measurement collapses. The refusal is not arbitrary or mysterious in the sense of being beyond understanding. We understand precisely why quantum mechanics does not provide clear pictures. The mathematics is clear. The experimental confirmations are overwhelming. What we lack is not understanding but visualization, and I have come to see this as appropriate. Visualization is a tool adapted to the classical world. It is tremendously useful there, but it is not fundamental to physical understanding. Mathematics is more fundamental. Predictions are more fundamental. Experimental verification is more fundamental. I have spent much of my life helping physicists make peace with this situation, helping them see that the lack of clear pictures is not a failure but an insight. Nature at the quantum level is genuinely different from nature at the classical level. Our brains evolved to deal with macroscopic objects where quantum effects are invisible. We should not expect our visualization capacities to extend naturally into the quantum domain. What we should expect is that careful mathematical reasoning and precise experiments will reveal the actual structure of nature, even if that structure defies intuitive visualization. And so I say to you, nature refuses clear pictures not out of malice or opacity, but because the quantum world simply does not have the kind of definite, continuous, visualizable structure that classical pictures presuppose. This refusal is itself information, telling us something profound about the nature of reality at its most fundamental level. Learning to think without pictures, learning to let mathematics and experiment guide us into territories where visualization fails, this is what it means to truly understand quantum mechanics. It is difficult, counterintuitive, and unsettling, but it is also honest, rigorous, and true to what nature is actually showing us through countless experiments over the past century. The pictures nature refuses to give us are pictures she does not have to give, because quantum reality is structured differently than those pictures assume. And recognizing this, accepting it, working with it, that is the path to genuine understanding of the quantum world.